And we're live. Yeah. How's everyone today? I'm hoping good. I'm hoping perfect. Yeah. I'm a little distracted today because I have a lot going on, but that's not a problem. We'll figure it out. We have an hour to hang out and do some stuff. Let me know when you join on. There's a, as always, I always encourage people when you join on. There's a link in the description to our Discord community. Feel free to join us and see if you have more questions and such. So I think what we're going to do today is we're going to work on this PR that we opened yesterday. We opened a PR yesterday on our Zephyr custom. Let's actually do this custom. Well, we didn't open a PR yesterday. We've had a PR open for a while, but I wish to extend it a little bit more. I wish to add some more feature set to this. So what we did yesterday is we managed to figure out our synchronization issues, and that came down to setting out the correct pointer to the inference service and having this inference service free the correct pointer. So that's what we managed yesterday. It was just a matter of doing this. Is this inference? This is an audio. So here we put in an address to the inference block, and in the inference service, we put in we freed this inference block that we got, and we also observed that the FIR filter actually did work yesterday. So what I intend to do today is actually, rather than do an FIR filter, I would like to transform our signal and use FFT. And the reason I want to use FFT is that this is more widely used when we are doing signal processing, especially in the wild. And as well, I think FFT buffers are going to be smaller than the real time, or rather the time domain samples that we have right now. So at least we're going to have made the samples smaller. And we can hold a representation of the data, and it also helps because we don't intend on playing back this audio. We really just intend on surmising some information from it. We're going to make a summary of information. We want to detect first of all, we want to detect whether a clap happened, which we're we're already doing in some sort of weird way. And then we also want to detect whether a clap happened, and we want to check later. We want to spot a keyword being said. And when I say spot a keyword, I mean we want to implement functionality like "Hey Siri." Basically, we would like our microphone to catch someone saying something like "Hey Siri." That's what we want to eventually do with that. So what I wanted to do today was actually change this from applying a finite impulse response filter to actually, we're using the FIR filter to apply a low pass filter. We're using FIR to apply a high pass filter, or rather, is it a band pass? I think it's a band pass, if I'm not wrong. It's a band pass filter. So we're passing things between, if I'm not wrong, it's something like, I can probably find out on the Discord. Let me see if I can find out on the Discord. Yeah. So let's bring in the Discord and see what we can find out. We can find out that we're applying, I believe it's a band pass between 1,500 to something like, oh my God, this is a long way up. Oh yeah, amazing. But I don't see it. Yeah, here it is. This is what I wanted to show. So I believe we are applying a band pass, and we're passing the cutoff frequency is 2,000 hertz and the high frequency is 6,000 hertz. So we're just passing the stuff that's in between that band. That's what we are passing. So That's what our FIR filter is doing. But we want to start computing the FFT of the signal, because later when we get to doing MFCC, we're going to use MEL MFCC coefficients. MFCC feature extraction. So we're going to use, I'll just go to the wiki. MEL frequency spectral coefficients. And we use this when we're going to detect when we're going to spot a keyword. And the way we do this is we start with taking the Fourier transform of a windowed excerpt of a signal. So the first step is actually to compute the Fourier transform, the FFT. Well, a Fourier transform is just Fourier transform, and then an FFT is a fast Fourier transform, because Fourier transforms take quite a bit of time. So an FFT is just a FFT. So there's a fast Fourier transform is an efficient algorithm for computing the discrete Fourier transform of a signal. So that's what we want to do. Basically, what we want to do today is just see if we can end up computing the fast Fourier transform of our signal. I think we're going to use something like shall we use the real one or the complex one? I'm kind of confused. Our signal is coming from the time domain, which makes it a real signal. So I think, but in essence, at the end of the day, every Fourier transform is going to become a complex one. So it's just the real one is stored more efficiently, if I recall correctly. Let's see. So that's a complex one, but we do have real ones. We do have a real oh wait, is it deprecated? That's odd. So we have complex ones, transform for complex ones, real FFT, those real FFT, they're still here. So the ChemSys DSP includes specialized algorithms for computing the FFT of real data sequences. There it is. Our audio signals are real data sequences. The FFT is defined over complex data, but in many applications the input is real. And real means you have like real value. You have like all those Gaussian steps. Like it's not 0 or 1, it's 0, 0.001, 0.002, all the way to 1. Okay, cool. So that's kind of takes the real part for us. The FFT is defined over the complex data, but in many applications, the input is real. The real FFT algorithms take advantage of the symmetry properties of FFT and have a speed advantage over complex algorithms of the same length. The fast RFFT, it's a fast, real, fast Fourier transform. What is wrong with people at ARM? Okay, anyways. The fast, real Fourier, the fast, real, fast Fourier transform algorithm relays on the mixed radix of C complex F. So basically, everything eventually is a complex FFT. But if we use the real one, it's going to be a little faster. Cool. I believe there's an example somewhere. I did find an example. I did find some sort of example. And actually, let's see. This uses CFFT. We can actually just click through all of this and find something that uses RFFT, and then we can go with that one. That's really what I want to see. I want to see something that initializes it, and then kind of goes with it. So this, yeah. And it's good to explore these examples, because sometimes you spend a lot of time figuring out something that's already been figured out, and that's not a good thing. Life is better when you stand on the shoulders of giants. I'll stop for questions at some point. But we can adapt the complex one to the real one, I expect. I think we can. And at some point we do want to actually plot our signals, but I haven't figured I know how to, I have an idea of how to get the signals to GNU plot, but I don't know how to get an actual signal and a filtered signal. I know I can send them in such a way that I can send two sets and one set can go to one plot and another one, but I have to design a thing. I have to design it somehow to do it, or maybe there's a way people do it already. Linear interpolation, okay, cool. Matrix example, I think we'll just use something with complex. I don't see RFFT in here. Let's see. I don't see RFFT. I think we'll just use the binning example. Yeah, we'll just use the binning example. I think the frequency bin example. So because this uses complex FFT, and I expect setting up a complex FFT, which eventually this is the same as setting up a real FFT, basically. And this is sort of the example we're going to use. We're going to need very, very few parts of this example. So first of all, I need to know, process that. How do you set it up? Where are you setting it up? That's what I need to know. What do we need to init it? Or maybe I just need to look at API reference and then transform functions and then real functions, and then I want the FFT over F32, this one, and then this should give me enough stuff. So I need this initialization, this one, and I need the initialization. I need to initialize, if I remember correctly from my other code, how we did it before. So we need to make an instance of the thing, and then we need to initialize it, and then at some point, once we have the data, we need to apply the FFT transformation itself. So just initialization and applying the size of it. So that's that. Do we need an instance of some sort? Is there a way? Do we need an instance? We might need an instance. Why wouldn't we need an instance? So let's see it does need an instance. You see this? This is an FFT. So we do need some sort of, I think it's here, FFT. And it takes an instance, yes. And then it also takes the length of length of the real sequence. So the length of our block. We have this already. We can transform to this already. So let's actually read this. ARM RFFT fast init F32. The parameter, I'm going to stop for questions just now. The parameter FFT length specifies the length of the real FFT CI complex IFFT process. Supported FFT lengths are 32, 64, 128, 256, 512. It seems to be a power of 2. There seems to be a problem. Because I believe we have an issue here. Because I believe our length is this samples per block. Samples per block is not, maybe not what we expect it to be. So cd Zephyr project. Any questions so far? No questions? No? Okay, cool. City, let's go to Zephyr project. Zephyr project, and then applications, and then we go to, what do I believe I want to go into? I would like to go into applications. I want to go to Zephyr custom BLE service, and then I'm gonna git status. Yeah, that's where we are. And So what I want to do is I want to go into the inference service and I want to find out what the samples per block is. I know. So sample frequency is how much? Is 44,100 divided by 10. That is 4,410 times number of channels, which is 1, is 4,410 samples. Which actually brings us to the next problem. Well, we might not be able to do this straight shot. We might start needing to batch this. Because look at it here, look at it here. So valid. This is one of the first times we've read the documentation as we were going for it, and it's actually changing quite well. Cool. It's really helping. Let's look here. The parameter FFT length specifies the length of the RFFT CI FFT process. Supported FFT lengths are 32, 64, 128, 256, 5, 12, 10, 24, 2048. It's all factors of whatever, factors of, it looks like 8. It's not 2. So I want to do this. Yeah, calculator. Let's see how we can do this. Let's try and figure out how we can do this. By the way, if you have any questions, do feel free to ask. I'm quite all over the place today, so 4410 divided by 32 is equals. Is it going to be 137? Let's see. 4410 minus 1496, 314. Is Bartholomew on? I need your expertise here, Bartholomew, if you're on. I'd like to know, if I remove 314 samples, will this affect my computation that much? Do I lose that much if I remove 314 samples out of 4410? If we lose 7% of the samples, do we lose that much data that we would lose? Can I truncate? Can I do it for the middle 4096 samples? So I remove 314 divided by 2. So I remove 157 samples from each end. Will that affect what I'm doing? It seems to me like this is where being bad at calculus now actually actively affects me now, because I need to figure out whether can I just do it for the middle 4096 samples? And that would mean I'll give it a length of 4096. That's fine. And then what I would do, when we probably will remove that. What I would do is let's go and look at the application of this, because I will hand it a thing so that it can do it. Yeah, this is the initializer. I see now. So you can initialize it to that. Perfect. Okay, cool. So initialize a 4096 one. And then once we initialize a 4096 one, we can just do this where we points to a fast instance, points on input buffer, points on output buffer. A value 0 is this is inverse, this is RF528, so 0. I can just do it. I can just drop the first 157 values and then give it a value of 4096, and then it will just do the 4096 and we should be okay. I can point in here where I do it, here where I apply the FFT thing, instead of going for samples F, I could start at samples F here. I would go samples F something like 157. Or I can just drop the last. I don't know if 300 is enough to like change everything. %. We can't lose that much. Can we make block sizes to go to 4096? Can we make can we do mem block sizes? Mem block. So it holds 4096 samples instead of 4410. Mem slab. Zephyr mem slabs. Let's go to Zephyr mem slabs. Let's look at Zephyr mem slab, and there is a limit. They need to be. Now this is where I'm gonna be. Yeah. The memory slabs buffer must be aligned to an n-bar entry where n is a power of 2 larger than 2, or power of 2 larger than 2. 4410 works, 4096 also works. I want to go back and change it. I would like to go back and change it. I would like to go back and I wonder how this changes our sample rate, or if it even affects anything. What happens if I go back to our audio header? So what happens if I go back to our audio header and I do, yeah, that's actually how I navigate. What happens if I say if this, rather than going that, what happens if I do this and I give this and then I say 4096? Let's find out. For argument's sake, let's actually find out what happens. Let's run this and see what happens. Yeah. It's gonna be source. Let's just run the Zephyr Zephyr project, and then it's the VM virtual environment for Zephyr I'm trying to run. Bin activate. You don't have to remember all of this. You don't have to remember all of this. So I'm gonna try West build HP NRF52840 dongle. and then NRF52840. Yeah, that's the one I want to do, and then I want to do a pristine build. Pristine build. Look, if we just get data out of this, I'm going to naively assume that that data is going to be okay. And then I'm going to go and proceed on obtaining the FFT of our signal. Does this mean we are skipping clap detection and we're just going all the way to keyword spotting? I think it would be much more interesting to just go straight to keyword spotting. I think so. I think it would be much more interesting to go straight to keyword spotting, which also introduces a new problem, or something I've been thinking about for quite a while. And Joshua from work actually hinted at something that could work, because when you want to run keyword spotting, you basically want it to run all the time. You know, you want it to run all the time, but that's a very expensive operation. How do you just run keyword spotting the whole time and save battery? That's a big problem. We might have to figure out a way to get the MCU to sleep while the microphone is doing something. We can't do that because we don't have a neural unit. And we can't really sleep the MCU because we're using a Nordic device which comes with its own power management. So that's a problem. An opportunity, not a problem. It's a good time to learn some stuff, I reckon. So first of all, it seems like it builds. It seems like it builds. Let's just run it and look at the logs and see what the logs say, yeah? But in order for me to run it properly, I need to... Did my mouse die? No, my mouse didn't die. Control R, and then I need to do something like --HW. This is a long, ugly command. It's from here. The easiest way to look at that command is from here. NRF. Yeah, the command I just typed in that looks... This command that looks so ugly is just this. Sorry, my internet is slow. I live in a farm in the middle of nowhere. Man, I don't even have fiber. I have to use like they have to go on a hill and they have to put an antenna on a hill. And then I have to point an antenna from my house to the hill and then I get Wi-Fi somehow. I need to find out what it is anyways. I don't want to find out what it is, but I get Wi-Fi. I get internet. I don't need that much internet. It doesn't need to be fast. I can do stuff. So the command I just ran is this. And this is the reason I'm running this command is because we can't really just West flash because the device we're using does not have an onboard debugger. So we can't just say flash. We have to do some sort of DFU update. I like this thing. Little hardy thing. Cool, so let's pack it into, we've called it FFT, aptly. I need to find a USB cable. Amazing, so let's run that. I'm putting that cable on the floor here somewhere. Not on the floor, on my desk. There's too many microcontrollers in the space, so sorry about that. Pardon me. It should be on, and I hope I have a phone here that can connect. Yeah, cool. Let me put it in bootloader mode so that we can actually upload Control R DFU FFT.zip.tymcmo. Yeah, that's cool. Let's load it up. So let's flash it. Bartholomew, are you here? I need some help with FFT. screen, yeah, SCM0. Yeah, cool. So that's fine. This is okay. This should work. Yeah, it's fine. Find the problem of looking on your phone. Things are happening on your phone. So when you look on your phone, you get distracted and start doing something else. Humans are so perceptible. Like someone can just take over our attention like that. Insane. Cool. I'll connect to this device. Okay. Initial discovery. It still works. The memory slab works at 4096. It doesn't affect our intention very much. Because remember, in order for us to compute an MFCC for a signal, we want to spot a keyword. A keyword like, let's be crazy. We want to go like, Jarvis, do this for me. We want our microcontroller to respond to that. And I watch Iron Man. I want to build Iron Man. I want to be Iron Man. Surprise. I think everyone watching this wants to do that. So I would like to talk to the microcontroller and have it listen to me. And in order to do something like Jarvis or Hey Siri or Hey Google or Okay Google or all of this keywords, in order to do that, they usually come to around 300 to 400 milliseconds of data. 300 to 400 milliseconds of data is something in the ballpark of 16,000 to 17,000 samples. It depends. It really depends on this. It really depends on your sample rate. Where's my code? So it really depends on your sample rate. We are sampling at 44,100. Nothing is stopping us from sampling at something like 22,500 or 21,500. 22,500, 25. Half of that, or even half of half. Nothing is stopping us from sampling at that. So it's just the more you the richer you sample, the more accurate data you're going to have. Sort of like. So we've fixed our first issue, which is our FFT implementation. You can do this, by the way, you can do this by yourself in C if you want. I believe I have a library. I believe I have a DSP in C. Yeah, I have some attempt here. There's an attempt here where I actually tried to compute everything by myself in C. But I was doing this as a method of like kind of getting familiar with signal processing and such. Ideally, I would encourage you to just go stand on the shoulders of giants. Go and use Kimsys. I'm not saying don't learn how it works. Really, try and really be very attentive to how they do things and how it works and all the internals. Because this is the thing. When a client comes to you and they want you to do this, they won't want you to do this the way it's done in the examples. So if all you know is how the example runs, it's going to be very difficult for you to achieve something that a client wants in custom. So by all means, attempt to do it by yourself. By all means, try and write the code. That will kind of open the doors to how other things are being done by themselves, and you can go do that. I find the thing that I always find is that I always attempt to write it. Even if it's just a simple implementation of how it works, I always attempt to write it. And then I usually get like a quarter way or a third of the way, and then I stop. And when I stop, it's because I have realized how it works, and most of the times I can actually even go and contribute to Kimsys, or it's an open source thing. Kimsys DSP. So Kimsys DSP is an open source thing, and you can go to GitHub and find it there. Where's the GitHub? Kimsys GitHub. So I encourage you, yeah, here it is. And it's actually not Kimsys DSP. DSP is in the name because it's legacy. This whole thing is called ARM math. It's, or rather, optimized compute. Or, yeah, here it is. Kimsys DSP is an optimized compute library for embedded systems. DSP is in the name for legacy reasons. That's how I started. So you can come in here. And you can open issues. You can do pull requests. They're all welcome. They're quite good. Just do stuff. Always do stuff as much as you want. So go see how they implement stuff. Try and help them do it in whatever way. So I encourage you. So what led me to say that? What led me to say that? Yes, we will use Kimsys DSP to apply this. So we were looking at the logs. So we've sort of fixed our thing for ourselves. It works. We get the samples. They're 4096. 4096 should cover the surface area we want. It's good. We can now move forward towards trying to attempt an FFT of the signal. What I was saying is you can do it yourself, or you can stand on the shoulders of giants and do it with them, but I would encourage you to deeply understand how it's working, so that when something needs to work in a custom way, you can just go and change it by yourself, and it should work out really easy. Okay, cool. So let's actually go to the subject of the video and try to actually do a thing where we do it. I would think we would need to init. Yeah, we need to init it. And var instance, this is just the name of the thing. It's just an instance. Cool. So we can actually just go straight into the code. This is quite simple. We can do it. Yeah. You don't have to do that. Just fine. It's fine. Everything now just sort of works because this has changed. This is now changed. This has changed to 4096. Let's actually write a code here. Let's write some comments here so that if someone is using this and they're later not confused, swapped to 4096 because our FFT implementation demands that. Basically what we're doing here is an approximation. We could have used all that. We're just using an approximation. So let's actually go back now. Now we can now actually go and do this. Let's do it. So in here we would like to make we can remove all of this. We can remove the FIR work, but we'll remove it in steps. So let's actually now define an FFT thing. And then each time we define something, we can remove the other one. So I can say ARM FFT. Ooh. I probably need to do transform. Let's actually look. Okay, config search. I probably need to pull in the transform library. Let's look at it. Kimsys transform. Kimsys what is it? Kimsys no. Kimsys DSP. Yeah. So I need to do DSP and then transform, something like that. I probably need to activate it like that. DSP transform. Yeah, transform functions. and they depend on Kimsey's DSP, and and it implies Kimsey's basic math. So that's fine. So actually, let's that's fine. We will as we remove everything else, we will remove this, and then this to do has already been done. There's no raise functions anymore. So actually, let's do, and this will error out actually if we haven't. Let's just see how it goes. Yeah, DSP transform. That's fine for later. We'll get to that. Where's the example we were looking at? We were looking at some example. So here we want an instance. Okay, our FFT instance F32, something like that. RMR FFT instance. And then this is going to be an n. Yes. And then let's call it FFT inst. Okay, let's do that. And then let's go back and remove this guy. Let's remove this one. And then we want to remove this one anyways because the parent for that has gone. Okay. So we would like to initialize it like that. That's fine. And it looks like in ours one, we do have a FFT size, but we can just use our sample block size, so it's fine. And then that's all. Yeah. Remember this. So init 4096. What does this take? Add in out. Cool. And then doing it itself. That's when we do it here. We say FFT len. No. Actually, the thing itself. This takes an in out. We can pass in this value there, but it's gonna be a magic value. So we can probably actually just define it as well. So let's define it here. Let's define is it an int? Yeah. Int FFT flag, something like that. I'll just FFT flag, and then we're gonna say this one is going to be value 0. So this computes the FFT itself. Okay, cool. I think the next time what we want to do is want to start plotting this stuff so that we can plot the row signal, FFT signal and such. I think that's actually what we're going to do, plotting live from the microcontroller, because now we're getting to a point where we're manipulating data but we can't look at it. It turns out today is some sort of like discovery session into where the stream needs to start going towards, the audio stream, not the other stuff, but the audio stream. Okay, cool. So actually, let's walk through this. So we've made a flag, and I was using this as a hint. There's something here that was hinting me. This was hinting me. This is fine. I'm not doing binning right now. I would love to do binning, but that's not the problem I'm doing right now. Maybe in image signal processing we'll do binning, but for now, let's look at it. So it looks like we want to do that. We want to do an instantiation of that. And why do they keep a status? That's also what I want to know. I guess it's for testing right now, but it's fine. We might. Do we need statuses? I wonder. Do we need statuses? We do need statuses. We need to know whether the initialization was successful or not. But this might be something we come back to later. We want to just try it right now. Quite a problem. Do they use the status at any point? So they just instantiate it and they run it, but they don't. They don't actually do the thing. So it's fine. I'll assume that it's a success. It's okay. And anyways, this is the length, isn't it? This is just the. What does this take? This initialize. We're going to do this. What do you accept? Initialize just the instance itself. Yeah, I'm okay with this. Let's try it like that. FAFO. You know what that means? Play around and find out. Cool. So that gives us an instance of the real FFT, and that will make it work for us. And then we just need to come down here, and we can actually do it. We can just do this, and that's the way we do that. Is just call. We've already initialized it. No, we need to initialize it. That's it. So we need to initialize it here. We sort of need to initialize it here. So let's see. ARM RFFT init, and I think 4096 F32 4096. So it's a fast one. Yes, I want that. And I have a feeling that added an import into my code. No, it didn't. Cool. Sometimes my code actions thing surprises me by how much it can do, you know. And in here, I just want to take an FFT instance. Do we want to take an address of the inst? Cool. And this is gonna be a warning because it's okay, sure. What? Yeah. So fast instance. It's a fast instance. RFFT fast instance. Okay. We're gonna find out. Fast. Fast instance F32 NY. Can I do that? Do you like it? Is that what you like? You're good. That's fine. Okay, so here, rather than filtering samples, we want to do compute FFT of samples. Remember, in the end, this is what we want to do. We want to take the Fourier. That's the first step, getting the Fourier transform, and then we need to now apply a few things, and then in the end we need to do like a discrete cosine transform move. This is actually doing the stuff. So we want to compute the FFT of the samples. Okay, cool. And the moment we compute this, we've moved from the time domain into the frequency domain, and we can operate chiefly in the frequency domain. I think. Okay, cool. So let's look at the example again and see if we can figure it out. That initializes it, and that takes that, and then we now need to do this, and then this just takes any instance, doesn't it? RFFT fast instant F instant 32. Yeah, that's fine. Hey, Fever's back. Excuse me. I apologize on that. Summer's coming and it's gonna stop. So. Shall I keep the filter and apply it later? I feel like I want to keep the filter and apply it later. But this is such expensive work. It takes so long. Am I not going to stray into some other... Maybe I can do stuff like posing. You know, an interrupt can stop like inference and such. But this is good. This is not... We're making up real-time problems for ourselves. And it's where the value of it is. Any questions so far? You can say hi, you don't have to say a question. Okay. So let's compute this thing. It takes an RFFT fast instance for F32. Is that what we made? An RFFT fast instance F32. That's cool. And we initialized it at the 4096. That's cool. So that actually fixes that for us. So ARM RFFT fast F32. So cool. So let's do that, and this will take the FFT. Actually no, it's you. Okay, let's just leave it at that, and we will come back to that later. So let's put a new line here. We'll delete that just now. ARM fast. What does it do? ARM fast F32. That computes the actual thing. ARM RFFT fast F32. F32. Yeah, this actually does something here. So, and then this takes our FFT inst. What the next thing it takes? It takes out a pointer to the input buffer. So I'll say samples F. Yeah. And then it takes a pointer, points to the output buffer. And then instead of calling this filtered samples, let's actually come back here and I kind of want to go to using I want to go to using a ring buffer, because this is kind of wasteful, having this many buffers that we don't use after we've used. I think I want to go to using some sort of ring buffer, so that I just use the ring buffer, and then when I'm done with it, I go back to another one. So okay, but for now, let's make it inefficient, and then we'll come back to it later. Let's just make it. Let's first make it work, and then make it efficient, and then make it fast or something. Let's just do the necessary for now, and I'll call it FFT samples. Okay, and then this will still be samples per block, and then that's there, and then that's okay. That's fine. That's now FFT samples. So in here, we want that, and then we want to go into FFT and then this want to go into FFT samples. Yeah, and then in here, I want to do samples per block, and then in here, we want to do that, and then the next thing we need to do is and then I need to terminate that, and then I need to come down here, and then I need to remove this, and then I think it's you, and then I'm pretty sure I need to remove that, and I just needed that as a hint, and then in here I would do I would just point at that instead of actually doing that, and then I'm gonna in here I'm going to say something like FFT sample. FFT sample. FFT sample, yes. We'll remove this doing the power measurement here. Cool, and this is what? Why do we have it? Okay, cool. Let's see. I-50 flag. Aha. We don't need samples per block. The reason being is because we already did it at our FFT instance already knows it's going to do 4096, and this is actually supposed to be I-FFT flag. We defined the thing just now to use here, FFT flag. Yeah, it's actually good that it just went straight to 0, so that's actually worked out for us. FFT flag. This should actually do it. This actually works. I believe this actually does it for us. Does it mean we're in the discrete domain or something? Let's run it. Let's run it and see what happens. First of all, does it even build? Any questions so far? Any questions so far? It would be awesome if it could. Okay, cool. That's okay. That's okay. We don't need the FR stage right now. It's silly because I've just deleted something that we might end up just using again right now, but it's fine. It's fine. It's okay. Just make things work. Break things every day and make them work. That's all you need to do. Break things every day and make them work. I'll check on messages a bit while that builds. Um, when this builds and it actually gives us an FFT signal, we can stop the stream there. It's been an hour. It's quite a busy day for me today. It's just always a busy day, and that's a lovely thing. I really love it. I like doing a lot. I like learning a lot. It's really awesome that I can just stop my day and go like, yeah, let me spend my day just doing this, figuring this out. Compounding is a crazy thing. You can learn a lot if you just do consistently small stuff. The hard part is just being sort of like consistent and keeping going at it, and you know, and every day you desire to do some sort of like groundbreaking new thing, but you know. I know. We can fix this. This is actually quite easy to fix. This is very easy to fix. I thought it was gonna be a thing, and I was like, this is, man. And as always, as with my streams, we've just discovered the debugging section. This is the danger zone now. Welcome to the danger zone. Let's fix it. I know it. I'm so glad I know how to fix it. We can go to project conf, and in here we need to requires full libc. Do we really need full libc? Anyways, I know what we need to do here. It's what we did here. I mean, we discovered this. Since it's DSP transform, that's it. This will enable stuff for us, and we can keep going. Because why? Because we need both of them, and yeah, that should actually build. We're probably soon running out of RAM. No, not RAM. No, because this goes in flash, so it's fine. We should have enough space. We should have enough space. But the build is definitely going to take longer. It's going to be something like an 800 or something. 669 from 617, so it's cool. That actually indicates that it might probably work. Any questions? Any questions? Let me look at the Discord. Maybe there's people with questions on Discord. No questions so far. Yeah? Okay. Okay. Alright, no questions on Discord, no questions here. That's cool. That's fair. Everyone's going. Everyone's good. That means either I'm doing something very boring that everyone understands, or I'm not streaming. I think I am streaming because I'm seeing people online, or I just completely lost people and I'm doing something that like no one can figure out what I'm doing. And that's another good thing because it means I'm doing it. I didn't explain myself well enough, but today's been a busy day. I understand if everything is confusing and such. Some days will be like that. Some days will be hard. In fact, most days will be hard. Actually, no. Most days are not hard. Most days are fun. I believe this should get it building. I believe this should get it working, and then we can stop. We can stop for today and be happy about what we got done. I would really love to see those FFT signals, and then I would really love to take some time and figure out how to plot them so that we can actually work on, visualizing the signals rather than looking at numbers. Looking at numbers is our brains are not very good at like determining what numbers mean, and we still have enough flash. We have a lot of the RAM is getting iffy. Whoa, that's a lot of RAM. I think we can actually fix that by using a ring buffer, because we can reuse the ring buffer safe. Like, look here in our code here, inference service. Look at this. You see all of this? This is 3 buffers of the same size. We can just roll through them. We can just use a ring buffer. Replace. I mean, you lose the original data, but what are you gonna do? Okay, let's run this and see if we actually computed an FFT signal. If it works, we did what we promised today. We did. Went a long way around, but we did. It's built, so I need to package it into an FFT. Cool. There you go. It's in bootloader mode. Let's actually now flash it. And that should have killed this. That is fine. It's flashing. I can see it blinking in front of me. This RAM line is getting quite a lot, so we need to start thinking about how to get efficient at that. This is good. This is amazing. This is real-time development. This is figuring things out. We actually having real-world problems, and that's cool. That's cool. On a little stream. But a dude in Africa. Oh, don't tell me it crashed. This might be the danger zone. It didn't crash. We just started it late. Okay, cool. I'm so happy it's not the danger zone. We can do a lot of things to make that stuff reduced. I'm trying to connect to it on Bluetooth, and then we can figure this out. And then we're sort of in a place where I'm happy. Connect. Not good. Not good. So not good. Not good. Not good at all. We are computing it, but it's all ending up at 0. That's not a good thing. That is not a good thing. And that is not a good thing. That is not a good thing. We never have any information in there, so... Okay, so we discovered a problem. We actually ended up, we ended the stream in a danger zone. That's what we've done. We're going to have to end the stream in a danger zone. Because what is happening here is, by some way, our computation is just making everything zeros. So at some point, we're doing something wrong with the data. Am I supposed to normalize things before I compute the FFC? I think I should. I really think I should. But I'm not sure. I don't remember that class. So I have to go and figure it out. Okay, but forgiving all the errors that we're seeing right now, we are computing an FFT for a signal, and although it's not working, I'll figure it out, and then we'll go on from here tomorrow. Thank you all so much for the 18 people who showed up today. It was really awesome, and that was amazing learning. We discovered quite a lot, and that was an hour of exploration of FFT signals today. Shall we write a comment? Yeah, let's write a comment. Get status. Git add prj conf git commit dash activate FFT signal. Activate FFT kim syslib git status git add src audio git diff dash staged. Okay, git commit dash m move FFT signal, move to 1496 samples per a block to be for FFT. Okay, git add src inference. Yeah, let's see, git diff dash stage. What is in here? Git status git add src inference. So git diff dash stage. We remove that, we remove this, which is git commit FFT signal broken FFT computation of signal. Bartholomew is gonna help us fix that, so I'm gonna git push and see what happens. Okay, and this code, it's in the description. The description of the video has a link to this repository, and all of this code is going to be in this repository. Thank you all so much for showing up today. That has been really amazing. I'll see you tomorrow with some more changes, some more things, and I'll probably have learned what I did wrong with the FFT, and we can go on from there. Thank you all so much. Cheers. Have a nice day. Discover some stuff, break some code, and learn some stuff. Cheers. Bye.